So once you've gotten used to where electrons are and that they can be exchanged, you've seen how to balance those compounds based on the charges they have. We're going to explain a little bit more detail now about how those electrons get exchanged. Some you may have an already understanding just from the balancing that we've talked about. But first of all, when two atoms get together, you should start to realize that there's different areas of the periodic table. When metals get together with nonmetals, for instance, that's called ionic bonding. And because they are stealing the other's electrons, they are held together with a plus and a minus charge, a full plus minus charge. That makes them very attracted to each other and more likely to be which phase? Right, the solids, because there's a plus and minus. They can vibrate when they get heated. That's motion is just what all that heat is. But they can't vibrate so much that they'll actually be able to move between each other and become fluid. So these are more likely to be solid. They're crystals. As a matter of fact, because they are plus, minus, plus, minus, plus, alternating pluses and minuses, that if you shift them even a little bit, instead of being plus and minus next to each other, now your minus and minuses are there. They'll shatter. That's what causes them to be brittle and to shatter into pieces. But they have high melting temperatures, okay, because they're tough to be able to get to melt. Covalent compounds, they're two atoms from the non-metal side of the periodic table, okay, from here it's on the right, and that you want that they share electrons. They have about the same amount of pull, so they don't get an electron, on one side or the other. They don't typically get charges built up on one, so they're not very sticky to their neighbors either. So they're more likely to be something like liquids or gases because they can move between. They don't have a strong force of attraction between one molecule and another molecule. They're more likely to be flexible, for instance, because the attraction between the molecules allows them to be dragged over each other. And they don't conduct. So that's covalent compounds. Metallic compounds are usually between two metals. They can be mixed in any portion because metals will always be mixtures. Because of the way they bond, they just share electrons equally. They're not that caring about those. That you can mix gold with cobalt, for instance, or nickel, and you'll make better gold or stronger gold or cheaper gold, 12 karat, 15 karat, 24 karat. They still will, though, be able to conduct electricity across them because they are loose about holding their electrons on, so even a mixture of metals, it'll still conduct electricity. Usually they're still high melting points because metal bonding keeps them from moving in between each other. They can vibrate pretty fast before they'll start to be able to swim through. One exception is mercury. They're still malleable. They can be pounded flat or drawn into wires because of the way they share electrons. Okay? So let's look at ionic compounds a little bit more from the idea from their outer shell electrons like we had done before. If I get a compound of calcium and fluorine, calcium's got 2 electrons in the 4s, and there's fluorine's got a 2s2, 2p5, so there's room for one more electron. If I take one of those electrons down here, and it wants to go in the outer shell here, this is going to then become calcium plus 2 ions, and its 4s is now empty, right? No electrons there. The fluorines are each going to have, I'm going to write 2 on the outside because that's an easier way to write this. They're going to have 2s2, 2p6, and this is going to become a -1 charge. Let me write that a little better. Okay, it has a 2s2, 2p6. Let the 2 out of there. That's going to be the way that electron transfer happened from the outer shell spherical path, 4 distance from the nucleus. It goes into one of the figure 8 orbitals around the fluorine. Now, in nature, you can't even tell because it's alternating plus minuses, 1 calcium, 2 fluorines, 1 calcium, 2 fluorines. There isn't such a thing as a calcium fluoride floating around by itself. It is just alternate, and all you can say is calcium and fluorine exist in a 1-to-2 ratio. Everywhere you look, there's a calcium and there's 2 fluorines, 1 calcium, 2 fluorines. So, and that's known as a formula unit. That's what the term for ionic compounds, smallest unit. We used to call them molecules up to this point, but they do have what are called formula units for ionic compounds. Usually only covalent compounds we're going to call molecules because there aren't a single individual C and 2 Fs. Now we can also show, instead of just showing the outer shell like we did in the electron configuration, where lithium, in this case, is going to react with bromine, I'm just going to show it again. This lithium is going to give its 1 electron up, go over here. Lithium becomes a +1 ion, bromine becomes a -1. That means that the 2s, the outer electrons right here, are 0. And the outer electrons here are all the 4s, the 4s and the 4p's are full. And so they're satisfied and there's electric attraction between them. Now there's ways that we could use those, but I think a better way just to show the outer shell, most atoms want to have how many? 8, right? So if we can use just dots around the outside of these atoms, we can show if they're getting close to 8 or if they're having less than half is 8. So if aluminum, for instance, which is in the third column over, has 3 electrons, I'm going to put in here 3 dots. There's a different way to show this, and that's going to be the way we use from here on out. Chlorine has 5 electrons in its outer shell. Sorry, 7 electrons in its outer shell. It's got the 3s2 and 3p6, 3p5. It'll look like that. 5 dots around here. It wants one more to be happy. And so when that does happen, I'll draw these in. 1, 2, 3, 4, 5, 6, 7. It's saying I just want one more electron. And I'm going to draw it as a different shape. Not that it really has a different shape. You can never tell an electron once it's left its atom. Let's try that again. Love when I used to use chalk, but those days are gone. Okay, that's the electron that came from the aluminum. And that happens to all of these, okay? And I'm not going to differentiate them here because they really aren't differentiable. So the aluminum ends up just becoming a +3 charge, and that's the best way to show these when you're reacting. Just show the metal is empty and it's got whatever charge it would normally have based on the top of its periodic table. The non-metal should be full of these compounds. It should have 8 dots around it. And that's the way you're going to show these ionic compounds. So take the time to work those problems and see if you can show the electron dots for this reaction.